Right, more live coding, Cannonball exercise. Let's have a look. Let's see what it says. It says a cannon is placed on a cliff overlooking the ocean. The idea is to fire on approaching enemy ships that attack the cliff. We need to calculate the angle to fire the cannon at to reach a particular distance. Okay, so there's a cannon. It's firing at ships, and we need to calculate the angle. Good, right, it's about the angle. The cannon always fires a cannonball at a velocity of v0. So velocity 0 is 100 meters per second. Okay, so the cannon has a certain amount of gunpowder, and that determines how fast the ball will, the weight of the cannonball determines the velocity, the initial velocity. Once the cannonball has been fired, there are no forces acting on the projectile in the horizontal direction. So we're ignoring wind and also friction, and only gravity in the vertical direction. Okay, so this is an ideal kind of cannonball. Below, we treat the two directions separately, and we ignore the third dimension. Yes, so we're not going to deal with the third dimension, which will make the cannonball go left or right. It's just going straight forward into the water. Good. Then it says, the acceleration at time t. So this is all about physics, and this is a common approach to these kinds of problems. X and y can be treated separately. And then there are three things to deal with. Acceleration, the change in speed, velocity, the speed, and position. And we're given all these things. The acceleration at time t is in the x direction at time t it's 0, because we said that it's not going to change the speed. There are no forces acting on it. So Newton's first law tells us that the force that acts on a body is equal to the mass times the acceleration. So we can actually calculate the acceleration from the mass and the forces acting on it. And if there are no forces, acceleration is 0 in the x direction, and minus g, so minus gravity, g is the Newton's gravitational constant, in the y direction. Good, that makes sense. Velocity is the integral of acceleration. Oh yes, so if you haven't done physics, this is just something you learn, that if you integrate acceleration, you get velocity, and if you integrate velocity, you get position. But the other way is actually easier to understand. If I take the position over time, it's some kind of curve. If I differentiate that, I get the tangent at the angle at a certain point. That's the rate of change, and the rate of change of position is speed. And in the same way, if I plot the velocity as a curve and I calculate the tangent, that's the rate of change of speed, which we call acceleration. In some sense, it's simply the definition of velocity and acceleration. So velocity is the integral of acceleration. So if we integrate this, we get the velocity. Since the horizontal acceleration is 0, the horizontal velocity stays constant. The velocity at time t is v0, so the initial velocity, times the cosine of theta. And the velocity in the vertical direction is, whatever that is, the integral of that. But why have they added this cosine theta if it stays constant? Well, the reason is that we've broken up this velocity into two components, the horizontal and the vertical. And it all depends on that angle theta at a certain point. So here it's going down, the velocity is going in this direction, but there's a y component and an x component. So we're simply using Pythagoras' theorem or trigonometry to get the x and y components. Not Pythagoras' theorem. It's simply trigonometry. And then we can integrate these equations to get the functions that describe the position over time. Boy, oh boy, I'm making this more complicated than it is, really. Okay, right, let's see. Once again, if we take the derivatives of x and y with respect to t, we find the velocities. Yes. So if you ignore the cosine theta for the moment, if we integrate this, we get back to that. Sorry, differentiate this, we get back to that. Oh man, I'm making a mess of this. Does it matter? Do I need to understand it? Well, let's see. Maybe I do. In this scenario, we have only one variable to control, the angle theta at which the cannon is fired. Yes, we want to determine the angle. But remember that the initial y-coordinate of the cannon is h. It's on the cliff. Yeah, okay, so x is maybe 0, but y is the height of this cliff, h. And this is 0y, the sea level, where the ship is. So we must use yt over time is the velocity times time plus h minus that thing, which is simply this velocity plus the h, this position plus the h. Okay, so let's just recap. Let's forget about cosine and sine. If we start here, this is the initial position, v0 times t. And when t is 0, we multiply this and we get x at time 0 is 0. If we just take this first part and we differentiate it according to time, we get v0. And if we differentiate that, we get a 0. And the same for the y position. Ignoring the sine theta, if we take this component and that last part, and we differentiate it, we get v0 minus gt. So the derivative of this story is minus gt. And if we take this and we take the derivative according to time, we get minus g. Right, good. Okay, right. And this is just adding the height of the cliff. And now it says the total time for the cannonball is tf. Final time is z squared, z plus, I can't read. We're solving this equation, yes. So we're using the quadratic formula to basically solve that equation, and we get this whole complicated mess. Do I need to understand any of this? It complicates things. But they've given us a lot of functions and the final time. Write a program Cannonball that accepts two real command line arguments. The height of the cliff, that's h, and the initial angle a, that's theta. Yes, we cannot control the height of the cliff. There are multiple cannons on multiple cliffs. Yes, sure, you can specify the height. Your program must display the cannonball at 0.5 second intervals and stop when the total flight time tf is reached. Okay, fine. So I calculate this. Can I do that? I've got the initial velocity. That's 100 always, I said. I've got a, I've got g, I've got h. Cool. Okay, right, good. So I know what the final flight or the flight time is, total flight time, and I just calculate these positions using this formula, yt and xt. Seems like it. Okay, good. What is g? Do they say? No, they don't really say. So we'll have to look that up, but it's just the gravitational constant, which means the force, the acceleration, or rather the force with which the Earth is pulling on bodies. Okay, fine. So we can look that up, and we just have a loop. Starts at T0 and carries on until we reach TF. And every time we print the X and Y positions. Okay, fine. I think I could do this. Just need this formula, and this top formula. Good. Right, let's do that. I'll probably want to keep. Oh, I probably can't keep. Never mind. Never mind. Right. Let's see. Two command line arguments. The height. It's probably a double. Args 0. That's the height. And also the angle. That's theta, but I can't write theta, obviously. Okay, let's calculate TF. TF is equal to. Oh, I'll probably want to calculate Z first. Yeah, let's do Z first. Yeah. So let's do Z. It just makes the TF formula simpler, I think. Now I've got to remember what it is. It's the initial velocity, that's 100, but let's make that a constant. Public static final double V0 is 100. So it's V0 times the sine of A. Sine of A. But I can't write this, of course, because A is in degrees and math.sine wants radians. So math.2 radians. A. There we go. No, A. Stupid eclipse. TF is, that's the formula, Z plus the square root of Z squared plus 2GH divided by G. Z plus the square root of Z squared plus 2 times G times H, and all of this is divided by G. Capital G because it's a constant. Let's do that. And you can look it up, but G is roughly 10 on Earth. Other planets have different G's, different gravitational forces, which is why on Mars you can jump really high and go really far because the gravitational force is lower because Mars has less mass and gravitation depends on mass. Okay, and then we have this loop. So I'm going to have T start at 0. And while T is less than the final time, I'm going to calculate X, double X equals, and the formula for that was X is V0 times T times cosine of A. V0 times T times the cosine of A. You know, it'll be easier to make A radians once, and then we don't have to use this construction all the time because it's not going to change. If it was going to change, I would not do this, but can't type today. But I think our life will just be easier. A in radians. A in radians. Okay. Y is equal to, let's see the formula. Same thing with sine, but we also add the height and we subtract this term that comes from gravitation. So, sorry. So it's V0 times T times math.sine of AR, but we also add the height and we subtract G times T squared divided by 2. Let's just double check if that's correct, because I can easily see that I've made a mistake here. So that's wrong formula. V0 times T times the sine of AR plus the height minus G times T squared divided by 2, that's subtracted. And X, let's double check, V0 times T times the cosine of AR. Okay, I think that's correct. And I see here at the end it also prints the final XF and YF, but we'll do that in a sec. And I see they use 2 decimal points. It's probably, we've learned how to do that, so I'm going to say system.out.printf t equals, did they use a double equal sign? No, single equal sign. I want to do exactly what they asked. 0.2f x equals 0.2f y equals 0.2f. So if you're just watching on YouTube and if you're a beginner, you probably don't know what on earth this means. But in my course we've done this, and it's simply a way to control how many decimal points are displayed, or exactly how something is formatted. If you use printf, it won't make a new line unless you include the /n end of line, and we just make t half a second more, and then I'm going to repeat this for the final time. Eclipse is not complaining, so I'll just shut my mouth. So it's, as you can see here, it's entirely possible that we stop here because the next time frame would have been past the final. The next time point would have been past the final time. But it is interesting to know the final time because it differs quite a lot. This is not a surprise. We've hit the water. Okay, right. All I want to change here is that. And I want to make these XFs. TF, 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 TF. The G stays, H stays, AR stays, V0 stays. And this is just printing. Okay, right, let's see if it works. I'm going to run it once. It won't run. It'll complain. I haven't specified command line arguments, but we can do that easily. Run configuration for Cannonball. Arguments are $string prompt. We've done this a million times in class. Let's run it now. I forget what the numbers in that example was. I think I recall this. Doesn't seem quite accurate. Oh, because it's 120. Okay, right. Let's run again and see if we get the same numbers. Okay, let's see. We fire the cannonball time t0. We go up to time whatchamacallit, and the numbers are very close. They're exactly the same, except for TF. I mean the X's, but the Y's are very different. 120, 131, 140, 147, 152 instead of 151. I have a 152 on this side. 154 is wrong. Okay, that's the peak. It went as high as it could, 150 meters, and now the cannonball is coming down again. So one more little fact that I didn't even mention: when we shoot the cannonball, it goes up if we have a positive angle, up and then comes down, and this follows a parabola. The fact that it's a parabola comes from the equations. The fact that if we integrate a constant twice, we get a second degree polynomial. But let's see here. So why is this so wrong? Well, the answer is easy. I lied to you. Gravitational constant Earth is about 9.8. Let's look up the exact value and we can be sure that we get the right answer. Gravitational constant. Will this thing tell me? That doesn't look right. I don't want to ask Siri. Okay, 9.81. So this is tricky, but this is a different gravitational constant used in a different formula of Newton. We don't have to talk about that now, but this is the one we want. 9.81. 9.81. We save, we run again. Okay, and let's go back. Cannonball. What answers do we get now? I can see here at the end we get essentially exactly the same answer. There's a small difference. Maybe this program used an even more accurate value for G, but it's negligible. It's maybe a centimeter out, so that will be fine. Yes, that's it. This is the last of the live coding videos that for this course. I want to continue making live coding videos, but they'll probably be a little more advanced. But I like them; they're fun, and I write a lot of programs, so I will be doing more of them. But thank you for watching all of these. Good luck with your programming.